Hello folks, this video is made for one reason and one reason only, which is to say that students freak out when they see that there are so many right-hand rules in their study of electricity and magnetism. So what we're going to do is basically introduce you to a fundamental idea, which is that the right-hand rule is basically a decision maker. In other words, I've seen so many students who kind of freak out when they see that there are so many right-hand rules, and I've seen other students who basically understand the right-hand rule because they understand one fundamental question, which is to say that what is the decision to be made? Those students who understand what is the nature of the decision to be made in each situation, understand the right-hand rule and become very comfortable with it. Those students who do not actually have discomfort with it. So let's go ahead and address exactly this question. And we're going to address this question by showing you three different circumstances and asking what is the decision to be made in each of those circumstances. Once you understand what the decision to be made is in each of those circumstances, you'll basically be able to be very comfortable with the right-hand rule. So the first place that the right-hand rule occurs is in a situation like the following. Okay, so you have F vector is equal to Q times V vector cross B vector, for example. In any such circumstance, the issue really is the following. You have V vector, you have B vector. You can have any V vector and any B vector you like. You basically bring V vector and B vector so that their tails are conjoined as shown in the figure. Now, the important thing to realize is that the resultant V vector cross B vector will for sure be perpendicular to both V vector and B vector. That is shown to you in this figure out here. Okay, so it will be perpendicular to the resulting F vector will necessarily be perpendicular to the plane formed by V vector cross B vector. However, what is the decision to be made? The answer is that any vector that is perpendicular to this plane could either be pointed in this direction or it could be pointed in the opposite direction. That is the only flexibility left behind. And the right-hand rule basically tells you to curl your fingers from the direction of the first vector towards the direction of the second vector as shown in this figure out here. So your fingers are being curled from V vector towards B vector, and you stick your thumb out, and the direction that your thumb chooses is indeed the direction in which the resultant V vector cross B vector should be pointed. In other words, this is the right direction, this is the wrong direction for this example. So let's go ahead and reinforce this. Suppose you have a V vector that is oriented this way, or you have any vector that is oriented this way, and it has to be cross-producted with another B vector that is oriented this way. Okay? And these two vectors, V vector and B vector, lie in the plane of this paper. We know that for sure V vector cross B vector will be perpendicular to the plane of this paper, but it could be perpendicular coming out of the plane of the paper, or it could be perpendicular going into the plane of the paper. Which one do you actually choose? And the answer is that you take your right hand, superpose it on this plane of this paper, and curl from V vector towards B vector, and that tells you that your thumb should be sticking out, and therefore this is the right choice. On the other hand, if you had V vector this way and B vector this way, notice that in each instance we basically conjoin the tails of the vectors. Then you have a situation where you have to again make a decision between the magnetic field, the V vector cross B vector, the cross product coming out of the plane of the paper or going into the plane of the paper. And you basically say that that single decision about whether it is going in one direction or the other direction relative to the plane that contains v vector and b vector is made with the right-hand rule. In other words, in this latter instance, you curl your fingers from v vector towards b vector. Notice that the direction is reversed relative to the diagram that we made above, and therefore we have this as the right decision to be made in this situation. So it's basically, the right-hand rule is basically a decision maker which only makes one decision. In other words, if you have a vector cross product, it is guaranteed that the resulting cross product vector will be perpendicular to each of those original vectors. That is already decided by this right angle that you see out here and this right angle that you see out here. The only decision that is to be made is whether you're going in this direction or in this direction, and the right hand rule basically helps you with that. Okay, so that's the first situation where you have a right hand rule when you have a cross product. So remember, cross products require right hand rule to help you make one decision and only that one decision. Now let's go ahead and take another situation where we had a right hand rule. Here, we're told that the magnetic dipole moment associated with a flat planar loop like this one, or a flat planar loop that is a circle, it doesn't matter whether it's a rectangle or a circle, is just given by the number of turns of wire in that loop times the current in that loop times the area of that loop. This is basically a scalar product, and anyone can evaluate that based on the information given. The only question is which way is n hat pointed. Now notice again that n hat is a unit normal vector that is perpendicular to the plane of the loop. So n hat could actually either be pointed this way or this way relative to the left top figure, and then that's when the right hand rule steps in, and it helps you to decide between whether it's pointed one of these ways or the other way. And that's where the right hand rule tells you to curl your fingers in the direction of current flow and around this flat planar loop, and therefore stick your thumb out, and the thumb chooses this direction, and therefore you draw your unit normal vector in this direction. So it just helps you to make a decision about one or the other choice of direction for the unit normal vector, but it doesn't make the decision about the direction of the unit vector itself. The unit vector, which is perpendicular to the plane of this coil out here, could be going this way or this way. That is already set. All that the right hand rule does is it tells you that this direction is wrong and this direction is correct for this particular loop that is being shown to you. Likewise, for this particular loop that is being shown to you, notice that it has some shading indicating that this direction, this part of the loop is towards you, this part of the loop is away from you, and therefore you go ahead and curl your fingers in the direction of the current flow and realize that the direction of the magnetic dipole moment ought to be like this and cannot be in the other direction. So let's go ahead and practice. You have a planar loop, okay, carrying current in this direction. There is no choice about this matter, which is to say that the magnetic dipole moment associated with this current loop will either be going out of the plane of the paper and perpendicular to the plane of the paper, or going into the plane of the paper and perpendicular to the plane of the paper. In other words, the choices are coming out of the paper or going into the paper. And which choice do you make? And the answer is that you curl your fingers in the direction of current flow, which is this direction. And so you curl your fingers in this direction with your right hand and stick your thumb out, and the thumb chooses to go out of the plane of the paper, and therefore you say that this is the right direction. and this is not the right direction. If, on the other hand, you had a loop that is entirely contained in the plane of the paper again, and this loop is carrying current I in this direction, then you basically go ahead and say that again the decision to be made is whether the magnetic field and the magnetic dipole is coming out of the plane of the paper or going into the plane of the paper. And in this case, you have to go ahead and curl your fingers of your right hand in this direction and then stick your thumb out. If you do that, you get to the realization that in this instance, this is the right direction, namely the magnetic dipole moment and any resultant magnetic field that is produced by this loop will be going into the plane of the paper. Same is true for a circular loop like the one shown at the left bottom. Okay, so this goes ahead and clarifies the issue that is under consideration when you're trying to make a magnetic dipole moment associated with a flat planar loop. Namely, you're going to try to make a decision about which direction of normal vector, n hat vector, you should be picking. And n hat vector is already guaranteed to be perpendicular to the plane of the loop. The question is that there are two possible perpendicular directions, and the right-hand rule tells you which direction is the right direction or the correct direction to be picking out. So that takes us through the second situation where a right-hand rule basically acts like a decision maker. Okay, but you have to ask yourself, what is the decision to be made? And that's what is resolved out here in this transparency. Now let's go ahead and move on to the third situation where we have the right-hand rule acting like a decision maker. Here, imagine, if you like, that you have current flowing in this direction as shown in the figure. Then what is the decision to be made? It is guaranteed that if you have current flow in a wire in this direction, so if this is a wire which is carrying current in this direction, it is guaranteed that the magnetic field will make loops around this wire. The question is whether the magnetic field makes a loop like this or whether the magnetic field makes a loop like this around the wire. Okay? Notice that those two directions, one going in this direction as shown, or another direction which is going in the opposite direction like so. That is the only decision that we have to make based on this situation. Okay, so it's guaranteed already that the magnetic field around this wire will be cutting loops. So let me go ahead and erase some of the things that are marked up out here. So that's the only decision to be made, namely magnetic field going like so as shown in the figure, or magnetic field going in this direction. But it will certainly be loops of magnetic field. That is guaranteed already. The decision to be made is the direction along which the loop flows, which basically determines the direction along which the line integral in Ampere's law will be carried out. Okay, so it's kind of an important decision because it helps you decide on how you will carry out the line integral. And for example, in this instance, we put our thumbs in the direction of the current flow, and then we curl our fingers around, and our fingers tell us that indeed this is the right direction in which the magnetic field is to be, in which the circulation of the magnetic field, which is B vector dot ds vector along the closed loop, namely this integral, is called the circulation of the magnetic field. So it tells us, the right-hand rule tells us that this is the right direction in which to evaluate the circulation of the magnetic field. This, on the other hand, is the wrong direction in which to evaluate the circulation of the magnetic field. So imagine, if you like, that we have a long current carrying wire. The bottom line is that the magnetic field associated with this current carrying wire is always going to cut circular loops around this current carrying wire. So if you have a current carrying wire which is carrying current out of the plane of the paper, the magnetic field is going to make loops. The only question at hand is, will it make a loop going counterclockwise or will it make a loop going clockwise? And to make that decision, you stick your thumb in the direction of current flow, which is out of the plane of this paper, and your fingers curl counterclockwise if you're using your right hand, and that tells you that the direction in which the circulation of the magnetic field ought to be evaluated out here is in fact in this direction. On the other hand, let's say you have a situation where you have current flow into the plane of the paper. It is still guaranteed that the magnetic field will make loops around this current carrying wire, that is an infinite current carrying wire carrying current into the plane of the paper. That the fact that it makes loops is guaranteed. The only question at hand is whether those loops will be oriented counterclockwise or clockwise. And that decision is actually made for you by the right hand rule, where you stick your thumb in the direction of current flow, namely stick your thumb going into the plane of the paper, and then curl your fingers around to realize that the direction along which the circulation of the magnetic field ought to be evaluated is this way. So in the top figure, the magnetic field will be like so. In the bottom figure, the magnetic field will have reversed and it will be like so. Okay, so that is the only decision to be made, namely, in which direction is the circulation to be evaluated? In which direction, on the other hand, is B vector dot ds vector along this closed loop, namely this guy out here, to be evaluated? And the direction is determined by the right-hand rule. The fact that there are circular loops around a single isolated infinitely long current carrying wire is already determined by observation and experimentation. So this gives us perspective on how to apply the right-hand rule in 3 different circumstances. But in each circumstance, ask yourself, what is the decision to be made before you go ahead and start fiddling with your right hand. Now, for exam purposes or test purposes, feel free to come to the test with 2 or 3 or 4, 2 or 3 differently colored pencils if you must, so that you can put one pencil along the direction of one of the vectors, put the other pencil in the direction of the other vector, and therefore decide on the cross product or whatever it is that you have to do. So we can't forbid you from coming to the exam room with differently colored pencils. Go ahead and use those pencils to actually visualize the vectors that you have to deal with, and hopefully everything will go well. So thank you very much. Hope you all do well, and hope we have a little more clarity with respect to the right-hand rule and the different circumstances where the right-hand rule is applied. Talk to you then. Thanks a lot. Bye-bye.